All right, here's the last one of these for a while. 10-4, inscribed angles. And quite possibly the strangest rule we're going to learn about circles. All right, it's about when angles fall in circles kind of like this. Randomly, seemingly, but there's actually some interesting relationships that happen. Yeah, you notice the vertex of the angle is on the circle, and then when we make an angle from any vertex on a circle, the rays of that angle are going to intersect the circle in two places, and then there's an arc that's on the interior of that angle. And those things have names. An inscribed angle is what we're talking about here, angle 1. It has a vertex on the circle, and the sides are chords. And the intercepted arc is that part of the circle that's in the interior of that angle. So this, I don't know if you can tell, it's kind of light blue. You know what, I can do this. The inscribed angle is this thing. The intercepted arc, I think, is almost the more interesting part. This is the intercepted arc. And the inscribed angle, I mean, technically the angle is these rays, right? So you could think of it as this. But we're talking about the relationship between that orange thing and that yellow thing. Okay. The theorem here is what's interesting. Actually, I shouldn't get rid of that. The theorem here, which is really surprising, the fact that this actually works is kind of crazy, that this angle is half of the degrees of this arc. So this orange thing, whatever it is, like it looks like it must be about 80 degrees or so, or maybe 70 degrees. Let's say it's 70 degrees. That means this thing here is going to be 140 degrees of the circle. Okay, so what does that mean? Well, let me show you this in Sketchpad. All right, I made this in Sketchpad so I can wiggle this around and you can see kind of what's going on. So here's the angle we're talking about. This angle up here is 73 degrees. And this arc CA, is 147. So if we took this times 2, we'd get exactly that. And what's kind of interesting is, so let me make this angle smaller. Make the angle more like 100 degrees. Sorry, the arc, 100 degrees. I've got 100 degrees of arc now. I've got about 50 degrees of angle. And that's always going to be, this arc is always going to be double this. So this is about 40 now, and this is about 20. And what's kind of interesting is I can move this around. And notice how the angle size doesn't change as I move this. As long as the vertex is on the circle, and it's intercepting this same arc over here, it's going to have the same size angle. That's kind of surprising. I left these rays on here so you can kind of see what's going on with the rest of the angle. Maybe it helps it look like it's the same size. I don't know. And so if I make a slightly bigger arc, so this is, let's make a nice number. Say it's about a 100-degree arc, 50-degree angle. Again, I can move this around. Angle size doesn't change. If you want to compare an angle to an angle, remember this arc CA here, this degree comes from the size of the angle at the central angle. So you could also think of it this way. This angle here at the center, this angle, well, what should I call it? Angle D is twice as big as angle B, no matter where I move angle B. Until I move it inside here, then wacky things start to happen. We'll talk about why maybe later. Notice the size of the angle now is huge. Well, it's not intercepting the same arc anymore. But when it's intercepting this yellow arc, I don't know if you can tell it's yellow, the measure of this angle over here is half the measure over there. Okay. Right. Next page. All right, so here's some more theorems about the same thing. So remember I was just moving that around in Sketchpad. It's almost like we could then take snapshots at 2 different points of that, and those angles will have to be congruent. Notice the angle inside both of these. Angle C, where's my, okay. Angle C is this blue arc here, or blue angle here. It's intercepting green arc DA, and this red arc B is intercepting green arc DA. So both of these angles are half of the size of the green, half of the measure of the green arc DA, so they must be equal to each other. Next one, if we intercept perfectly a semicircle, so inside angle G here, you can kind of forget about this FH, that doesn't really matter really at first. The arc that's inside angle G is 180 degrees, so this angle has to be 90. It often looks like this though, like the way they have this pictured with the diameter. This makes a right triangle because if you know this is a diameter, then we know this is 180, which means we know this is 90. So it's kind of a nice picture that we make it. So yeah, whenever you make a diameter and then you connect that at the ends of the diameter to any point on the circle, it has to be a right triangle. This has to be the right angle because this has to be a semicircle because of the diameter. Nice little theorem. And last one, quadrilateral is inscribed in a circle. I'm going to do this in Sketchpad again. The bottom line here is that the red angle marks are going to have to be supplementary, and, oh, let's make a different color. The purple angle marks, oh, they're not congruent, so these could be 4 different angles. Ooh, that's 3, and this is 4. None of these angles have to be congruent, but the purple set makes 180 and the red set makes 180. Let me show you that in Sketchpad too. All right, what's going on here? This is all related to the theorem we just learned about with the inscribed angles. If you think about angle B right here, angle B is half of the measure of the arc it intercepts. So angle B, this arc right here, this angle right here, this is half of the arc that goes from C, because this is part of the arm of angle B, to angle E, which is over here. So B is half of that thing, and the angle opposite it would be D. So this angle over here is half of, okay, angle D is this angle here. So it's half of this arc here. So these two red things are half of their opposite big red things. Does that make sense? So what's going on is that the angle here is half of this arc, angle here, angle D is half of this arc. Well, I know what these two big arcs have to add up to. The two big arcs have to add up to 360. So when I cut them in half, whatever they are, like it could be 160 and 200. When I cut them in half, I'm going to get things that add up to, guess what, 180. And that's going to happen at the other angles as well. So each one of those sets intercepts arcs that comprise the entire circle. So their sum must be 180 each. Oops, sorry, I'm on the wrong page. So yeah, the arcs of L and N add up to, the arcs that start at M and end at K both ways, end at K both ways. All right, you can rewind. I don't need to say that over and over again. You can just rewind and look at it. So let's do some actual problems. Here's the fun part. All right, so find the measure of angle ABC. This would be a little measure, I think. Find the measure of angle ABC and X. Well, if this is 20 degrees, then this has to be 40 because this angle C here intercepts this arc here, so that's 40. If this is 40, well, this has to be 20. I'm just filling in things that I know. If this is 110, is there any angles that intercept arc CD? Oh, there sure is. There's an angle right here. This angle at B, angle CBD. You can tell by those letters, CBD. Measure of angle CBD. When C and D are on the circle, and B, actually when all three of them are on the circle, you know that B is the one that's half of the arc that connects C to D. So if this is 110, this is 55. I mean, you can look at the picture, of course, but that's always going to be true. What else was I supposed to find? Oh, ABC. ABC. Oh, I've just accidentally kind of done all that because I found this 20 and I found this 55, so this has to be 75. I could probably go around the circle and find more stuff, but I won't. I'll leave that for fun time in class. All right, find X, Y, and Z. I'm not going to target any one of those. I'm just going to go around the circle and find whatever I can and start writing things down. All right, if this is 51, this might come in handy. I know that 51-degree angle opens up to this. When it hits the circle, it hits at F and H. So that arc from F to H is 102. When this 27 hits the circle, it's going to hit a 54. Oh, this is a diameter. So I know, F to C is 180 both ways. So this is 180 over here. So this is 78. This is a right angle from that diameter property we talked about. We can have 180 on this side of the circle. So if this is 54, this is, let's see, 126. Is that right? To make 180 over there. So I've got the whole circle spoken for now. So now this X, Y, and Z ought to be easy. Oh yeah, 54 there, 27. I could have known that because angle F and angle H hit the circle both at G and C. So even without knowing the 54, I know that have to be congruent. This whole thing's 90. So if this is 51, this has to be 39. And Z opens up to this guy, so he's got to be 63. There's probably a ton of other ways to do that. I just went around the circle trying to find what I could find. I could probably find these angles also. Oh, sure I could, because 180 in a triangle here and here, yeah. And that's not a bad idea, actually. If I kept going and I found angles other ways, they should agree with the angles I found the first way. Like this 78, if I ever went back and figured out an angle that intercepted it, it ought to be half of that. Like if I want to do this angle down here at F, like CFH, it ought to be 30. Oh, look, there's a 39 here. I found it from the right angle, and it intercepts the 78. So, oh, good for me, it agrees. That kind of thing should happen. There should be some built-in checking as you do these problems on the test. All right, another diameter. So I know that this is true and this is true because dA is a diameter. If DC is 80, it's the open end of an angle here, so the other end has to be 40. Oh yeah, we know this too. Okay, first of all, angle D, sorry, not angle, semicircle from D to A, so this is 100. CA is congruent to BA. When you have congruent chords in a circle, they make congruent arcs, so this is also 100, so this is also 80. It's really bad, 8. But if this is 100, angle Y is opening up to that 100. I don't know if you've noticed this yet, but there's lots of times when you're looking for this angle Y and you're kind of focusing on this part of the picture, and the answer is actually way down here. Or the way to get this answer is in a completely different part of the picture. I got this 40 first thing I did because of this over here. So there's a lot of this like looking all the way across the diagram for something else and go, oh yeah, what I'm looking for, I've been focusing my attention down here, the answer's up there, or over here, or over here, over here. So it's my advice to you is back up, zoom out, and look around and start filling in whatever you can, and the answer may be farthest from where you're looking. All right, find x and y given that A is a point of tangency. If A is a point of tangency, oh yeah, there's kind of a special case of this intercepted arc rule that isn't really clear from this description. Let me go back to Sketchpad on this page. Remember this thing? I guess I don't need these. I can get rid of this. This is going to be in the way, I think. Actually, so is the center. Let's get all this out of here. Okay, so we said this angle here is going to always be half of the arc it intercepts. Even as it gets really close, B gets really close to C, notice how this arm of the angle starts looking more and more like a tangent as I get closer and closer and closer and closer. Turns out if it is actually tangent, if that's right on there, that's pretty much tangent. If I make it tangent, Sketchpad doesn't know what I'm thinking, so it doesn't know exactly where to put it. But I'm just trying to illustrate the rule here. When it is tangent, this rule still applies. It's just a little harder to see, but notice the angle hasn't changed. When I move that really close, the angle size of B is still 50.14 degrees, and it turns out if I actually do make it tangent, you just have to believe me, because if I go too far, look what happens. I don't want that. If I get right on the tangent, it's still true. So we treat angles at tangents just like angles like this. Some book would call it inscribed. Some books call it something slightly different. We're not going to call it anything different because we're not going to go any farther. This is the last lesson on circles, so we don't confuse you. Anyway, my point is, if this is x, this arc that's inside this angle is going to have to be 2x. And this angle over here is going to have to be 2y. Because it's inscribed, as if it were an angle like C or B. Oh, in fact, angle C and angle B are pointing to those two angles, just the way I kind of need them to. So if this is 60, this is 60. This is the arc opposite it, or the arc that's inside that angle. So that tells me what x is. If this is 2y, I know this is also y. Is that helpful? Maybe not yet. All right, if this is 140, this is inside this guy, so that's 70. This is 60. Oh, look, I got 180 on a line here. So if that's 130, I got 50 left. So let's just do it that way. Okay. And again, hopefully this all worked out. 70, 60. Oh, good, 50. I have 180 in that triangle. Excellent. Oh, I have about a minute left. Oh yeah, this is the opposite angles in a quadrilateral. So E and D add to 180, so this is 105. X and, well, this angle, whatever it is, have to add to 180, but I can find that. All right, so if this is 75, this is an inscribed angle in the circle. 75, that means this whole thing from here to here has to be 150. If that's 150, I know this part, 70. Yeah, and this thing's 105, so this whole thing has to be 210. And if this part of it's 96, the rest of it is 104. Why did that help? Well, just a second. I actually didn't need this 104. I care more about, let me pick color. I know from E to, is that a different color? Yeah, kind of. From E to D, it's the 84 plus the 96. That is what's intercepted inside of C here. So all of that actually adds up to 180. So it turns out this is actually 90 degrees. DE is actually a diameter. I'm almost out of time, so I'll make this quick. Isosceles triangle, fill in the symmetry. The whole circle is 360, solve for y, and the angles of x intercept each one of those angles of y, so they are half. And there's also other ways to get that. I will see you in class.